Good afternoon, everyone. As Tomislav said, I'm Nico from Politecnico di Milano. I'm associate professor there. And among the courses that I'm teaching, there is one which is entitled Creativity for Sustainable Design. What I'm presenting today is just a subset of the topics that I'm teaching there. But I'd say that this is the real initial step to understand where to act for eco-innovation. So I'm not repeating the title, but today we will go through the general logic which is behind LCA, and I will try to clarify why running an LCA at the very beginning of every innovation process can be the boost for making innovation, as it targets problems in terms of environmental issues and environmental footprint, environmental impact, so that one knows which are the problems to target in order to boost eco-innovation and to run eco-innovation. So let me start with a kind of provocative question. Should you have these two alternatives, which one would you pick? In order to be, obviously, maybe for the taste, you would go for the left side, while you would leave what you find on the right-hand side just for something that you need to grab from a coffee shop while you're walking or something like that, or maybe from a vending machine, while for the taste, what it's better, it's what you find on the left-hand side. But should you be environmentally concerned, which one would you pick for sure? This is a kind of rhetorical question, but the key point is that there is no key answer if one does not run an LCA to understand it. Because in the end, we know that the paper cup is a disposable one, while the one that we see on the left, which is a ceramic cup, it's something that you can reuse as many times you want. But at the same time, one needs to be washed, so water has to be warmed to clean it. You will need to use detergents. These detergents would go to the water streams, and then it pollutes the river, and so on and so forth. And for the production of a paper cup, it's something which is super simple. It doesn't require a lot of energy. While if you need to, let's say, bake ceramic, that requires super high energy. So do you have the answer? I do not, unless I run an LCA. So let's see what an LCA is. Well, actually, before talking about LCA, it is important to understand what a life cycle is. Every product has its own life cycle. So there is no product if we do not have some, let's say, raw materials to be processed, so that these can become semi-finished products, and then these can become the final product. So this is the production stage, but in the end, even the raw materials need to be extracted from the sources where they are available. So maybe minerals comes from mines, water comes from water streams or from the sea, cotton, like in this example of a t-shirt, needs to have some crops for cotton, so that then you can process the result, the harvesting, let's say, of these crops, and create cotton, so that then you can create textiles and make your own t-shirts. And this is just the manufacturing stage, but then there is a whole life. There is the other part of the life cycle. This t-shirt needs to appear on some shelves of some shops, and so there is a need for transportation. Then you buy it, you bring it home, and then you use it. You probably use it sometimes, not just once. You wear, you wash it, then you maybe iron it, and there is a certain amount of energy which is required to do all these things beyond other materials. Even for washing, as we said, for the cup of coffee, we need to use water, detergents, and so on and so forth, softeners maybe. Then products come to the end of life. Maybe this t-shirt gets some, it wears out. It wears out, and so once it's worn out, we need to throw it away. And where does it go? Well, maybe you can cut it and do some, pieces of cloth to clean your home, or maybe you throw it in the waste basket and then we don't know where it goes. Maybe there are opportunities to recycle it or to dispose it and then it goes to the landfill. And I'd suggest you to check what happens, for instance, in Atacama with all the waste that comes from the textile industry in South America. That's scary to a certain extent. You can see mountains of these fast fashion clothes that gets disposed there. But that's the life cycle. And obviously, this cycle, as I described it, it's pretty linear. Then we can try to figure out if there are opportunities to make this life cycle circular so that we do not need to get new resources every time, because in a way we are making our planet resources poorer and poorer from time by time. So if we manage to reuse them, we are somehow helping ourselves to get a sustainable future, not just us, but also the future generations. So the key point is that now finally we are concerned with the environment and the potential harm that we are introducing to the environment. The logic of life cycle thinking to a certain extent has started pervading many different laws and legislation that appear from time to time, and so on and so forth. Even the tools which are available to consider the life cycle of products and their potential impact on the environment has become more and more developed. So here you have just a general overview of what took place in the last 20, 30 years. Actually, the last years are some missing. This is an excerpt of a graph that comes from a paper from 2021. But this gives a clear overview of what is going on in the field. And so let's get to the key point. I'm a mechanical engineer. Nobody's perfect, and so I have my own defects. And typically, my way of thinking, the key to develop new solution, focuses on what we have on the top of this slide. So we think about how to make the products, the system, the manufacturing processes, or whatever, capable of delivering the functions as we would like them to do. So we also try to understand where to search for raw materials, how to manufacture product, how people should use them, and so on and so forth. So we mostly focus on what we see on top. But in the end, there is no such thing if we do not extract resources from the environment. We often say that we have no planet B, and in fact, we are making our planet A poorer and poorer. Like if there is a planet B. But the key point is that we are not just making it poorer because we extract resources out of it, but because we are also emitting harmful substances to the environment. So as a result of any anthropic activity that we are doing to bend the nature to our own will, because we want to have products which are capable of doing things which are not typically common, that do not pop up by themselves, or that nature does not provide us an answer for. So through these products, we are somehow impacting on the environment by creating potential harms to it, by making it poorer because we are getting resources, and by injecting again inside the environment things which are not that good, and we call them emissions and waste. So in the end, if we want to keep a life cycle approach, there is no chance to consider just one of these two sides, as we did in the past. There are obviously risks, but also opportunities for product development if we start thinking to this type of model for product development and for innovation in general. Because in the end, we will have a chance to develop products which are less impactful for the environment, whether because we manage to reduce the use of new raw materials or resources, or because at the same time, or together maybe, because we reduce the emissions and waste that we are releasing to the environment. Then the key point is that we can do this with a twofold approach. On the one hand, we can be purely qualitative, and so we can say, okay, let's use less resources, and that's enough. I'm already doing what I'm doing, what I can, because in the end, I'm reducing my impact by getting less as I can from the environment, or let's reduce the emissions. That might be enough, but to a certain extent, we need to understand also how much we are impacting on the environment, because it's not simply like that. Not all the raw materials that we are using have exactly the same impact on the environment. So a qualitative perspective might be not enough. So the qualitative approach, which is typical of life cycle thinking, it's a starting point. But if in the end, if we want to have something tangible, something that we can measure about how much we are impacting on the environment, something quantitative is needed. And if we want to go on the quantitative side of life cycle thinking, we need to move from life cycle thinking to life cycle assessment. And we will see what it is. Well, actually, it's there for a long time now. So I'm not talking about anything radically new. Life cycle assessment already exists for more than 20 years. It has been progressively more and more structured, and let's say norms and standards are now available to run life cycle assessment studies. Here you see two examples. Actually, these are the two standards that regulate the general principle and the way to use life cycle assessment as a tool, as a method, as an approach to figure out what are the environmental impact from a quantitative perspective. There are also illustrative examples on how to apply the prescriptions of LCA and to benefit from this example, also to replicate new studies, especially to run those stages which are more critical to carry out. We would see what they are right now. Actually, to run an LCA study, you need to go through 4 main stages. You can see them here below in terms of title. The first stage, it's called goal and scope. And within that stage, you need to understand what you are doing the life cycle assessment for, who should be benefiting from the results of your study, and you need to define what is the product system, whether it's a process, it's a product, but in the end, once you consider it from the perspective of the whole life cycle of it, it becomes a system because it interacts with many different sources, many different flows of materials, of energy, and obviously it interacts with the environment. So in the end, it becomes a system, and we need to decide what are the key flows within the system that we would like to consider to run our analysis, and at the same time, what are the boundaries for this analysis? Because in the end, we would like to maybe focus on the whole life cycle or just on a subset of it, and we would see how, in a while. And obviously, we need to understand also what are the geographical limitations of our study. For instance, is my analysis, my assessment valid wherever we are in the world, or it's something that, I mean, I'm from Italy, I'm in Italy at the moment, so maybe my analysis would just be focused on what is happening in my production plant with the manufacturers or the suppliers that I'm interacting with, and so on and so forth. So once I have defined the so-called goal and scope, and I have defined all these elements, the key point would be the so-called functional unit. We would see it in a second. We need to figure out what happens during the whole life cycle in terms of flows of materials and energy that concur, that make it possible for my product to take life, to be used, and finally to reach its end of life, whether it's a sad end of its life because it goes to the landfill, or it's a happier end of life because its components or its raw materials can be injected again in a new life cycle without making the available resources in the planet poorer and poorer. This is one of the key points in the whole life cycle assessment study, because it's probably the more time-consuming step within the activity, because you need to get data, you need to figure out where to find it, to quantify them, and describe the process life cycle so that it's robust enough to describe what actually happens without potential mistakes and this type of issues. But once you have it, then you need to go to the next step, which is the so-called life cycle impact assessment. And it's when you translate the effects that you have on the technosphere, which is what we saw before in gray color, into something that have an impact on the environment. And in order to do this, you need to understand what are the key impact categories that are relevant to your study. So would you consider CO2 emissions because you are concerned by climate change? Other type of emission, for instance, the emissions of ozone or the emissions of sulfurs, and so on and so forth, because these are all potentially affecting something that we would like to protect, to ensure sustainable development and make it sure that the ecosphere doesn't get spoiled because of the activities that we are running on the so-called technosphere. So by deciding what type of model we will apply to run the life cycle impact assessment, we will get some results. And these results might appear in the form of, let me switch this laser pointer, to this type of impact categories, or to something that concerns bigger categories, because the impact of all these activities one by one concur, or let's say potentially have an additional impact on the health of our ecosystem, on our own health as human beings, or on the reduction of available natural resources. This type of results then gets interpreted in the fourth stage. Now, as I said, it appears to be a purely linear process. So we start from goal and scope, then we go to the life cycle inventory. We understand what are the different steps in the life cycle of our product system, all the flows. We determine one way or another, it depends on the model that we are picking for life cycle impact assessment, and then we interpret the results. Pretty linear, but in the end, the reality, it's this one. We are running this study in it's not a messy way, but it's iterative. So because we figure out running this type of analysis that things are not exactly as we had in mind at the very beginning, because maybe we need to refine the functional unit, and therefore all the inventory needs to be fine-tuned depending on the way we are reconsidering the functional unit, and so on and so forth. So a short deep dive on what's inside every step. I tried already to describe a few of these things, but now let's see what happens during the goal and scope. At first, we need to define the objective of the study. So there are 4 key questions to answer. What is the question to answer in terms of environmental impact? So what type of environmental impact we would like to understand, and why? Why are we running the study? Why that environmental impact, why that question that we would like to answer matters, and to whom? So the audience who would like to read the study, because we are providing something which is not valid just for us, but in principle it can be used also by other people, and we need to understand who they are, because the results and the final report should be shaped so that those which we are targeting should understand it. And then we also figure out where we are publishing it to make it accessible for all those people. And these are general terms, general topics that define the objective of the study. But then we need to deep dive on the field of application, and we need to figure out what is the system, which is not necessarily the product, as I said, because it can be the process, it can be something that in the end will appear as a process, as the life cycle, it is a process, but it would be also describe a system, because there would be different things that interact with each other. And we need to understand what that type of system is for. So what's the function that it has? Because as soon as we figure out what is its function, then maybe we should shift from the product perspective to the functional unit, which is something that tells us what the system is for. A bottle of water, it's something that does not necessarily come as a bottle of water from the perspective of LCA, because if that bottle of water is potentially reusable several times, let's say a glass, a bottle of water made of glass, which is probably not disposable, but compared to a bottle which is instead made of plastic, the one which are actually disposable, can we really compare these two the way we want? It's pretty similar to the example we had with the cup of tea, the cup of coffee before. Well, it's not like that, because in the end, we need to figure out how many liters that bottle of water made in glass will be capable of holding through its whole life cycle, because in the end, it can be a comparison one-to-one, but it should be a comparison one to a multitude of plastic bottles. Okay, that makes a lot more sense, because we are not comparing the product per se, but the functionality, the usefulness that these two products deliver, which is the capability to hold water for some time. And among the field of application, we also need to define the time span that we are considering, as well as the system boundaries. So it means where our life cycle starts and where we expect it to end. We can consider the life cycle from the extraction of raw materials to the end of life, and this is called a cradle to grave approach, but we can focus on something which is maybe just in the middle of the life cycle, so excluding the raw material extraction and excluding the end of life. And then we focus on something that we typically call gate to gate. And it depends on where we define these boundaries. The gates might be larger and closer to the extremes, or maybe focusing on a very narrow phase of the life cycle, a very short phase of the life cycle only, which is far from both the extremes. Obviously, we also have combinations, which we can run analysis which are cradle to gate, or for instance, gate to grave. If we start considering the opportunities coming from the circular use of resources and from circular economy, we can also run analysis which are so-called cradle to cradle, so that we include the reuse of materials, their recycling, and blah, blah, blah. There are many other things to consider, but I think that these are the key points to touch to understand what we need to define in terms of goal and scope, so that it doesn't move. Okay, so that then we can see, according to the boundaries that we have defined, what type of data we need to gather and collect from the sources where these are available to describe what is actually happening from a quantitative point of view during the life cycle. In the end, we are interested in two main things: the resources we are injecting inside our product system and what we are emitting as the results of our product system. To understand it, actually every of these phases that we see here around, so from design to manufacturing to retail and use to the disposal and recycling or reuse, all these phases have inputs and outputs. All the inputs are considered as resources, all the outputs are considered as emissions. Within this framework, we need to understand what is happening, because these are the key elements to describe our life cycle and understand what would be the environmental impact. I do not understand why it doesn't scroll, sorry. Okay. The one you see here, I'm not staying on this slide for much time, but the key point is that here you see in boxes all the different stages that characterize a specific product life cycle. Actually, this is the analysis of an automobile shredder, but you see that these are the key steps in the life cycle of an automobile shredder, and it tries to describe all the different flows that you see as inputs and outputs. You see them as arrows. Every incoming arrow is a resource that we are using as a flow. Every outgoing arrow, it's an emission that necessary. I mean, if it goes into the blank space, as it happens here, these are really emissions. Sometimes these ones from one box move to another one. So we are having an input-output relationship. So in a way, what comes out as an emission of a box of this kind, it's not really an emission, but it's an output that becomes an input for the second stage. But here you have a clear overview of what it takes to run a life cycle inventory. You need to figure out how much, not just what are the flows, what are the resources, but also how much resource of each resource you need in order to get to the final product that you want, and to estimate these emissions. Then the third step concerns the translation of what we had here before, because this describes a model of the technological system that we have, and we would like to translate that type of model that we call life cycle inventory into something that tells us how much that type of life cycle is impacting on the environment. So we need to apply a model of the environmental system that explains what are the cause and effect chains that from the technosphere has an impact on the environment. Here you see an example for which we get from the life cycle inventory. And this is how the environmental model that we apply during the life cycle assessment work. We try to figure out what are the relevant impact category, which might be GWP, so global warming potential, ozone depletion potential, and so on and so forth. But we are trying to figure out what are the actual emissions, not something which is so generic, because in the end, every product, it's emitting something, not necessarily in the form of CO2. That's why we refer to so-called CO2 equivalent emissions, because every product emits something, and maybe we need to have a common layer of understanding those emissions. For global warming potential or greenhouse gases, we consider CO2 as the standard, but we should be aware that methane, it's actually more impacting than CO2 on global warming potential. Every methane emission, it's in any case estimated in terms of CO2 equivalent emissions. We get indicators for these categories so that we understand what can be the direct impact on the specific category itself, and then maybe we can try to put some of these categories together depending on what is the final endpoint that we would like to consider. For instance, human health, environmental health, resources reduction, and so on and so forth. And here you see how this type of mechanism work. This is probably even easier, because here we see in the blue column, the midpoint impact category. There are global warming. You can see how much water we are using, and we see that the combination of some of them concord to the so-called damage pathways that then result into the so-called endpoints, which are the areas that we would like to protect. We would like to protect human health, ecosystems, and resource availability. So it creates a link, and it tells us something that we couldn't estimate just by the analysis of flow through the life cycle impact, but that our LCA results can tell us, given the fact that we have a model that describes these potential environmental impact. The final step of LCA concerns with the interpretation of results. Actually, it's not just the interpretation of results, it's something more, because in the end, we are asked by the standard to check if we have something which is complete enough in terms of data, especially in the life cycle inventory. If these are, it makes sense that what we observed through the LCIA results compared to the LCI. We need to run some consistency check, and also potentially some check for sensitivity in case the data that we inject as an input for the life cycle inventory can have a degree of uncertainty or are just qualitative, and we made some quantitative transformation, and so on and so forth. So now the key point is why we are running this type of LCA analysis, in order to understand what can be done on the environment and to boost eco-innovation. Well, we do this because we maybe need to decide among different design options. We would like to decide what should be the decision. So how can we be supported in terms of product development to go for a product which is less impacting on the environment, or at the end of the process, we already have our product there. We need to declare if and how much that product is already emitting CO2 within its whole life cycle, because we need to have a declaration or let's say a certification that says the impact of my product is this amount. So let me start from something that can be, that concerns design. And so the very first stage of innovation, we need to innovate, and we need to figure out what can be the next product and what are the best alternatives. So should you decide what should be the best vacuum cleaner, how would you go for it? Would you go for something that has a standard filter? Would you go for something that works as a robot that we see here below? Or would you go for something that uses a cyclone filter? Which one is the best one? Well, in the end, we can start running LCA even from this stage, despite we do not have many data available, to understand what are the potential benefits of going into one direction or another one. So it's a support for decision making. The same stuff can happen as soon as we have defined what are the key working principles. Here we see two vacuum cleaners which are pretty much the same, because they are both using a cyclone filter, the ones which are now available everywhere in the market. But still, there are a few decisions to make. So where should I put my filter? Here you see the left and the right option, which have the filters placed in different positions. Do they work the same? Do they provide the same benefits? Do they have the same vacuum cleaning power or potential? And then, what are the final impact on the environment? Well, you can run it even in this case once your product is pretty much defined, to understand what's the best option to go for. Or your product is already there, and then you need to say something to the whole world. My product, it's impacting this amount on the environment. It generates this amount of CO2 equivalent kilograms, and so on and so forth. For this reason, actually LCA is the key, because actually both the environmental product declaration, EPD, the product environmental footprint, which is something that the EU is supporting as a standard for product certification in terms of emission, rely strongly on LCA. These are both methods which are LCA based. Unfortunately, here you have all the data, which is a lot, something lucky, but at the same time, it's a nightmare, because building the life cycle inventory with that amount of data, it requires a lot of time, and you need to get data from the whole supply chain, especially if you want to run an analysis which is cradle to grave. Maybe you don't need to design anything, but you want to innovate something on the organizational side of your company. And if you want to do that, the option, you have several options in front of you. You need to understand how you need to light up your plant or your, let's say your plant, what should you go for? Should you go for a standard incandescent lamp, which are not standard anymore, for fluorescent lamp, for LED lighting system? How should this be powered one way or another? So in terms of assisting decision-making for corporate sustainability, LCA is also the key. Because in the end, you can rely on already existing EPDs, so environmental product declaration, for this different type of lamps or lighting system, and run comparison. But here, once you need to run comparisons, the key point is that you cannot really compare one product with the other one, but you need to figure out if the function that a standard lamp, let's say fluorescent lamp, it's delivering, it's comparable with the one of an LED. Their lifespan, it's not the same. So maybe this is how and why you need to define the functional unit in a smart way so that it makes sense all in all. So I don't know if I'm running out of time. I kindly ask Tomislav how much time I have, because if you want, I can share an example to see how results from LCA can be used to generate new ideas or to prioritize problems in terms of environmental impact, or I can even stop here.
I think it would be nice to see an example.
Okay, so this example, it's not mine. It's something that comes from a paper. It's the paper, it's the one that you see here. It comes from the International Journal of Life Cycle Assessment. It's not that new, it's from 2016. And it describes an LCA of a horizontal axis washing machine in China. So they have to describe what is going on for that washing machine. And as functional unit, they picked the product as such. So this horizontal axis washing machine produced in China with a rated capacity of 6 kilograms and a lifespan of 10 years. Then it is a bit more than that. Sorry, it is a bit more than that, because you see that they have a pretty clear description of what this system can do. But they are assuming that the capacity of their system is 6 kilograms, and then they run the analysis assuming that this type of washing machine is loaded with 6 kilograms in these 10 years. This is not the best definition of the functional unit, despite it's a reasonably good one. Much better if you decide in advance how many washing cycles you run per year. Because in the end, from a functional perspective, you use the washing machine because you want to have clean clothes. And you want to have 6 kilograms of clean clothes every cycle. So it's important to say how many cycles per year, so that in 10 years you understand how many clean clothes you manage to get. This is a brief example. I mean, it's not very well described. This is purely qualitative analysis of the system boundary, but this is the key point to start the life cycle inventory. So we see that we have raw materials, which come in blue, and also the ones that has been processed, because these are in blue as well. The one which are in yellow background are coming from suppliers or from as raw materials. Then there are some internally developed manufacturing processes like injection molding, stamping and bedding, spraying, and blah, blah, blah. We managed to produce our semi-finished product that combines with the semi-finished product that are coming from the supplier. We put them together into our assembly that comes out to be our washing machine, which is the final product. This final product doesn't end here, because the analysis is broader. We are considering also the transportation, the use and disposal. So this is an example of cradle-to-grave analysis. And this is a general description carried out with one of the available software, which is Gabi. Here you see that the production stage considers the production of steel, of the bucket, of the cables, of electronic parts, the glass door, the counterweight in cement that is placed on top of the drum, and so on and so forth. All together generate something that is useful for the assembly. This is purely qualitative, what you see on the left-hand side. If you move to the other 3 boxes on the right-hand side, you see what are the inputs for the manufacturing stage, for the production of a washing machine, which are in blue color, and the one which concerns the emission, so something that we are injecting to the environment as a final waste or something like that, which comes in red. Now, if you see this data here, it's easy to understand what are the components which are requiring most of the materials within the whole life cycle, and the ones which are requiring most of the energy. The cabinet, which is apparently something which is not so demanding in terms of materials, in the end contains almost 19 kilograms of steel. It requires 11.5 kilograms of water that will never belong to the final product. But these are somehow wasted to a certain extent, whether in forms of water or in form of steam. We need some electricity and so on and so forth. And so we can do this type of analysis for all these elements. In terms of electricity, the parts which are requiring most of the energy are the plastic part, because we require 116 kilowatt hours of electricity, which is the top value among all the others. We are not yet understanding anything about the potential impacts. We are just analyzing the inventory. We can go on with the inventory. We see that there are also some data that are referring to the use phase and to the end of life. Something which is important is that whatever we manage to get out of our system at the end of life, that we can recover, should appear as with a minus on top, because in the end, this should be subtracted from all the materials that we are consuming from the environment. We are saving them from going to the landfill, then we can reuse them somehow. Then, if we want to estimate the final impact on the environment, we need to figure out what are the key categories, impact categories that we need to consider. For this study specifically, the authors consider the ones that you see here on the left-hand side, and you see that each, or maybe some of them that concerns chemical species or something similar to chemical species, some emissions are not estimated just in actual kilograms, but in so-called equivalent kilograms of chemical substances. So for acidification, we have SO2. For GWP, which is probably the most famous, we have CO2. For ozone depletion, we have CFC. But all of these are considered as equivalent masses of emissions, because in the end, we are not just emitting CO2, we are emitting CO2 and other type of chemical species. These are all, let's say, brought to the CO2, for instance, equivalent quantities by the method that we are applying for this type of impact assessment. In this case, the method that these authors used, it's CML from 2001. Now, some results. We are really to the final slides. Here you see what are the impacts of different stages in the life cycle. In blue, you see the production. In gray, you see the transportation. In red, we have the use phase. And in green, we have the end of life. And these are telling in relative quantity which of these phases it's the most contributing to a specific impact category. So what is the life cycle stage which mostly affects the emission of CO2 equivalent? CO2 equivalent are characteristic of GWP, global warming potential. So if I see what happens in this column here, the phase that the life cycle phase that mostly affect CO2 emissions, or that it's triggering CO2 emissions, it's the one that spans the largest part of this whole column. And it's the pink one or red one. And so we see that it's the use stage. Within a washing machine life cycle, the use stage is the one which is mostly responsible for CO2 equivalent emissions. So if we want to reduce that amount, that is my point, we need to focus on new ways of running the washing cycle and interacting with the washing machine if we want to get the largest benefits. Then as a second step, we should focus on production. While focusing on transportation doesn't help much because the savings that we can get from CO2 emissions are very poor. The same activity can be done in terms of the specific components, so something that actually helps designer to understand where to focus their priority. Should I redesign the whole assembly? Should I redesign the counterweight, the cabinet, the inner tub? Well, still with stronger attention on CO2 emissions, which is still the column GWP, the component which is mostly responsible for CO2 emission, it's the one in green, and we see that it's plastic part. Would I, in case I would like to reduce CO2 emissions for a washing machine, I should focus my attention on the plastic parts. I should try to reduce them as much as I can, maybe substituting them with materials which are less impacting on the environment, and so on and so forth. There is no key point in focusing on the inner tub, because, I mean, I can even work on that and reduce that impact, but the benefits that I can generate are definitely slower and smaller than the ones that I can generate if I work on the plastic parts. The same can be done for every category. Let's take this other example of ozone depletion. Here, the situation is completely different because the system parts which are mostly responsible for ozone depletion, so for CFC equivalent emissions, it's electronics. And so if I play on plastic parts, I do not get the same benefit that I would get on GWP. If I want to reduce ODP emissions, I should work on electronics and not on plastic parts, which also means that whenever we are doing something on one of these components, we are potentially triggering emissions on other type of categories. So that's why it's important also to iterate LCA to be sure that we are diminishing the impacts. Let me go for the last two examples. The phase, which is the impact category, now we are reversing it, which is mostly affected by the consumption of tap water. So tap water, here it is. It's to be searched among the columns where the green color appears to be more relevant. And so here we get to the ODP. So this is seen in a way in reverse. What happens if I reduce the use of tap water? What are the categories that I having more impact on? If I work on tap water, maybe I would manage to get more significant reduction on the side of ODP rather than on other type of categories, GWP rather than others, okay? And, okay, this is based on raw materials only. If I should focus my attention on which materials should I decide to work on for a substitution, for a transition to new materials, maybe I should search for the ones whose columns are larger in all the categories that I see. And so probably we should focus on the ones in blue and the ones in black or blackish, because these are widespread all over the different impact categories, and the same it's applicable for the black ones. So if we want to make our washing machines less impactful on the environment, less impacting, we should try to reduce as much as we can the use of steel and the use of plastics, maybe substituting them with materials which are less impactful. Brief summary, why we are doing this? Well, to support decision-making. LCA, it's the key point to start the decision-making process and understand where to look next in order to make our products less harmful for the environment in every life cycle stage. And that's it from my side. Sorry if I went a bit long.